Hello friends, welcome again in this session on DR analysis using SIGRA software. In the last session, we have already discussed about the significance of analog and digital channels in the disturbance report. We have also discussed about the methods by which we can analyze this analog channel and digital channels, how we can interpret the results from these analog and digital channels by using these two cursors which are displayed on your screen right now. Also, in the last session, we have discussed one DR, which is regarding the auto reclosure of one of the line, and only by seeing these analog channels, how we can determine the dead time of the remote end substation and dead time of the auto reclosure at local end substation. We have already discussed these things. In the last session, we have also discussed that how you can determine from the disturbance report that what is the breaker opening time, how much is the fault clearance time, how much is the relay decision time, what is sampling rate, what is the meaning of 1000 hertz sampling rate. These things we have discussed in the last session. In the last session, we have also discussed about some of the features of SIGRA software, wherein we have discussed that how by the use of these two cursors, we can determine the magnitude of analog signals, the instantaneous value, RMS value, the value in terms of primary, in terms of secondary, everything we have discussed in the last session. In this session, we are going to discuss about the circle diagram, which is basically the zone diagram, that is the boundary of zone 1, zone 2, zone 3, zone 4, zone 5, how it is drawn on the SIGRA software, which is drawn by default by using the disturbance report itself. And now by using this zone boundary, by using this zone characteristic, how we can determine that why at particular point of time zone 2 picks up, why at this particular time zone 3 picks up. Also by using this same zone diagram, we can determine that before the inception of fault, is there was an import of power or export of power. Also, what is the fault resistance of the fault, is everything we can determine using circle diagram. In this session, we will also discuss how to insert some analog or digital channels, how to multiply two analog signal, how to add or subtract two analog signals. Also, we will discuss about how to determine the fault location using the SIGRA software from any DR if you have some basic settings available with you like line length, R1 and X1 magnitude, then you can determine the fault location from the disturbance report itself. So now, without wasting further time, let us start with our today's topic. And in the last session, since we have already discussed about this DR and we are continuing with the same DR in this session, so I am not going to discuss again what is the various analog and digital channels in this DR, what are the meaning of these analog and digital channels, how we can interpret the results. That those things I am not going to discuss in this session. If you have any doubt regarding those things, then please watch last session, which is already available in the playlist. So go there and you can watch everything. So now we will start with our first topic, which is the circle diagram. So if you click here in your SIGRA software tools bar, this circle diagram will open, and here in this circle diagram there are three windows. One is for the phase to ground loop, another is for phase to phase loop, and last one is the active and reactive power flow on the transmission line or on the feeder. So now in this DR, if you can recall from the last session, that our fault was, and this is called time signal, our fault was in the A phase to ground, or as I was using the terminology in the last session, that the fault is R phase to ground fault. So now in the circle diagram, I am not going to select this L3E, which is B phase to ground or C phase to ground fault loop. I am also going to remove this L2E, which is Y phase to ground or B phase to ground fault loop. Now you are left with only ZL1E, which is R phase to ground or A phase to ground fault loop. Just zoom in this to 200%, and now you are having a better view of this zone diagram. Now I am going to remove each and every zone for the better understanding. So first, if you see, this is a blank characteristic of R and X axis. So first of all, if you click here, zone 1 boundary will be drawn, and this is zone 1, which is basically the 80% or the 60% of your physical line length, depending upon what setting you are using. Generally 80% of line length for all the transmission line except for series compensated transmission line, wherein this zone 1 reach is reduced from 80 to 60%. And I have already discussed about these theoretical concepts in our initial lectures, that is lecture 1, 2, 3, 4. And in those sessions, I have already discussed why this top line is slanted at some angle of 5 to 7 degree, why this line is not parallel to y-axis, or why it is drawn at some angle. Similarly, what is the meaning of this line and what is the meaning of this line, everything I have discussed in the first session on the basics of distance protection, and then the two different sessions, that is session 2 and session 3, wherein I have discussed about the effect of fault resistance on distance protection performance, and also the effect of pre-fault power flow and in-feed on fault resistance on distance protection performance. So if you have any doubt regarding these things, you can directly go to the playlist and watch these sessions. These are available in English and Hindi both. As you are aware that in my channel, all the videos are available in both Hindi and English language, and you may watch any session as per your convenience, and the content is same in both the languages. Now this is zone 1. If you select zone 2, now zone 2 will be exactly the same replica of zone 1. The only difference is zone 1 boundary is 80% of principal line length, and zone 2 can be 120 or 150% of principal line length depending upon your reach settings. And I have also discussed about this reach setting concept in the first session itself. So this is zone 2. And now if you can recall that zone 1B in case of Siemens relay is basically the reach is exactly the same of zone 2, and zone 1B means zone 2 plus carrier receive, that is carrier added protection. So now zone 1B, if you, I am removing zone 1 for the time being, and if you see here, this is your zone 2, and if you select, this is your zone 2, this dark green line, and now if you select zone 1B and just this blue line, which is exactly the same as zone 2, because the reach of zone 2 and zone 1B is exactly the same. Only difference is when carrier is received in zone 2, it will trip in zone 1B. This is zone 1. And now if you select zone 3 will be the exact replica of zone 1 and zone 2, apart from the fact that in zone 3 there are a portion which is cut out from this characteristic, and this is because of load encroachment, which already I have discussed in our first session, that what is load encroachment, what is its effect. So now this zone 4, which is reverse looking zone, so if you see here, all other zones are drawn in the first quadrant, and now this is zone 4 which is drawn in the third quadrant. Zone 5 is a non-directional zone having a large area. So now if you see this is the characteristic of the impedance, that is the V by I ratio, which is changing with respect to time. So now this cursor 1 I am going to use. So on the time signal list, I have selected this cursor right now at this point, which is prior to the fault inception. So now go to this circle diagram, and if I just increase this slowly, so now just see here, at this particular point of time, your characteristic is now entering from the right hand side to this zone impedance boundary. And why it is entering now at this particular point of time, if you go to time signal, you can see from the time signal that at this particular point of time, current is suddenly starts to increase and voltage is suddenly start to reduce, and because of the change in current and voltage, now your impedance changes, and once the impedance changes, the characteristic points moves inside the boundary, because now the ratio of V and I reduces. So now the characteristic in every sample it is going to enter. First it will enter in the zone 5, or which is a non-directional zone, and at this particular point of time your relay must pick up. So now if you see in the time signal at this particular time, you see here your relay has picked up, and this is just because of inaccuracies. So just see here, now your relay must have picked at this point in time. So your relay 21 has picked up. So now if you just keep on increasing the sample, at this particular time the characteristic enters into zone 3. It is not yet settled. So now keep increasing, and now at this particular time, now the characteristic has settled. And what is this point? Basically, if you zoom it further, you can see that this point is inside zone 2 characteristic. Zone 1, it has not entered. This is zone 2, and once the fault is in zone 2, if you remember here, this is definitely inside zone 3 also. So now from the time signal, you can see that at this particular time, your both zone 2 and zone 3 is in pickup condition, because if the fault is in zone 2, it must be in zone 3 also. So zone 2 and zone 3 both picks up. And now if you just keep on increasing, now just keep on increasing, the fault is in zone 2. Right now carrier has not received, so your resistance protection relay has not operated. Keep increasing, and now you can see that this characteristic is still rotating, but now slowly it exits from this characteristic. And why it exits? That means at this particular time your relay must have operated and breaker must have opened. So now if you see here, at this particular point of time, if just remove, at this point itself your breaker has opened. So at this point itself your characteristic tends to exit from this zone. So characteristic removes from this and your fault has already cleared. If you can see the same from the analog signal also, at this particular point of time your current and voltage is no longer available, and the relay has operated and fault has been isolated. Once the fault is isolated, now the characteristics moves out, and once the characteristic moves out, now it will settle somewhere outside, and after this dead time, you can say that the characteristic once again will settle inside this area. And why inside this area? Because if the pre-fault case, the power was being exported, so now again power will be exported, and we will see this power export from the Wavin software while doing the DR analysis using Wavin. But right now this is a very simple concept. You can just select any zone, you can zoom in these zones, and then by using this movement of the cursor, you can determine that at what particular point of time the characteristic has and the impedance locus has entered into zone 1 or zone 2 or zone 3, or for that matter zone 4. And then if that characteristic enters into that particular zone, has the relay picked up or not? If the relay picked up, then have the relay operated or not? So you can determine each and everything by using this circle diagram. So now let us move to the next topic, which is assignment of signals. So now in this case, first I am going to time signal graph. So this is my time signal graph, and in this time signal, if you see, there are 7 analog channels, which is I, A, B, C, N, that is current of phase A, B, C and neutral, and then the voltage A, B, C. So now if you want to add any other voltage signals, current signals, or symmetrical component signals, so just go to assign signals, and from here you can see that these are the default signals IA, IB, IC, IN, and you can have any other signals. So suppose I want to have a zero sequence current and negative sequence current in my DR. So what I have to do is just select this I0 at any, this is I0, and then select I2, or also select I1 if you want. And I'm just going to change these properties for better clarity. Suppose I have changed this characteristic or this line properties of I1, I2 and I3. Everything I am going to change. And the last one is I0, not I3. So I have changed I0, I1, I2 and just apply. And now you can see from your DR that on every channel there are 2 signals available. On the first channel, IA and I0. I0 is basically the zero sequence current. So just remove this IA and you will see there's only I0 current. Remove IB, you will see I2, and remove IC and you will see I1. And one of the important things that you can see from here is that your I0, I2 and I1, these are almost exactly the same magnitude order. And why these are exactly the same magnitude? Because this is a phase to ground fault. And if you can remember from the power system analysis that if there is a phase to ground fault, then your I0, that is zero sequence current, is equals to I1, that is positive sequence current, is equals to I2, that is negative sequence current. You can also determine the same if you select, suppose, IA, and suppose select I2 only and nothing else. Now you can determine that, suppose the cursor 1 determines your magnitude of IA current, and I am going to take this in the primary terms. So select this primary. At this particular time, your primary current magnitude of IA is suppose 5.75. So now just move second cursor to the same point. This second cursor is also at the same point, and select this as I2, and you can see here that the magnitude of IA is 5.75 and magnitude of I2 is 1/3 of 5.75, which is 1.95, approximately 1/3. And why it is approximately 1/3? Because in the phase to ground fault, I0 is equals to I1 is equals to I2. So you can determine these things from this assignment of signals. Also, if you want to see some another signal, you can do just that also. Suppose I don't want to see this I0, I1, I2. Instead, I want to see this impedance Z, R, and X. So you can see those things also. Just apply and OK. And now with IA, IBIC, you can see the ZA, Z, R, and X magnitude. And now at the point of fault, if I want to determine what is the magnitude of suppose X, so cursor 2, I only have to select. This is the magnitude of reactance at the time of fault. And if you know the magnitude of reactance at the particular time of fault, you can determine the fault location from this also. So now this is for the analog signal. Similarly, you can do for the digital signals also. What you have to do is go to analog signal. Suppose you want to see any particular signals or you want to delete any particular signal, just keep on removing these things from your DR. Suppose I remove some signals from here and then just apply and OK. So first of all apply and then OK. So now you can see that some of the signals might have been removed from your DR. So I have removed power swing, SOTF, and some other signals which are now not visible. If you want to remove this carrier receive signals also, just go here and just go down, and suppose I want to remove this 8521 receive also. So apply and then OK, and now this will be removed. So now if you see here, those two signals are removed. So like this, you can edit your DR. If you want to see any signals, or if you want to remove any signal, you can do in the SIGRA itself. Now comes the another important part of our session, which is how to determine fault location using SIGRA software. If you have DR available with you, then how you can determine this fault location. So first of all, I am going to edit or unedit this DR, just without saving, and I will open again. So this is the original DR. So again, if you want to determine the fault location from your DR, what you have to do first is go to option and go to network configuration. In this network configuration, since this is a Siemens relay DR with all channels properly configured, and you are viewing this DR in the SIGRA software itself, which is the part of Siemens Dixie software. So you don't have to do many work here, because once you are opening a Siemens DR, these IL and IA, IB, ICIN and VA, VB, VCVN will be automatically mapped. This primary current ratio and primary and secondary current ratio and primary and secondary voltage ratio will automatically come. Then inside the impedance calculation also, this value of RE by RL and XC by XL you don't have to enter manually, because this will directly take this value from the .rio file, which I have already explained in our last session. Next thing which comes here is the fault locator. In the fault locator, you have to enter something manually, and whichever first of this is, suppose this line length. Suppose this line is of 32 kilometer, and then you have to enter this resistance and reactance value, and then this RE by RL and XC by XL ratio. So this RE by RL and XC by XL is exactly this same which is relay has determined from this .rio file. If not, then you have to enter it manually from your relay settings. Then OK. And once you do this, go to view and then go to fault locator. And now this will take a few seconds, and after that few seconds, the relay will display your the fault location. And this is the fault location, which is 15.2 kilometer from our end, and 5 kiloampere is the fault current with fault resistance of 7.2 ohm. So in this way, you can determine the fault location from any DR if you have the only two settings available with you, that is the magnitude of positive sequence resistance and positive sequence reactance, and then the RE by RA and XE by XL ratio. If you have these four parameters available with you, then you can determine the fault location from any DR by using SIGRA software. So we will keep up to this point only. In the next session, we will meet again and we will determine the fault location from one of the DR, one of the MyCom DR or P444 relay DR. And in that DR, we will see in detail the network configuration, because for Siemens relay, network configuration is not required if you are using SIGRA software, although it will be required in WebWin. So once we will go to WebWin session, then we will see how it is being done. So in the SIGRA software, you have nothing to, you don't have to do anything for Siemens relay. So now in this session, we have already understood how to assign signals, how to use circle diagram. In that circle diagram, how you can determine the zone pickup by using your characteristic. There is zone 1, zone 2, zone 3, zone 4 boundaries. Then I have explained you this fault location determination using SIGRA software. And in the next session, we will meet again with some new topic of fault or DR analysis using SIGRA only. And thereafter, we will move to WebWin. So I hope whatever is explained in this session is clear to you. If in case you like the video, please share with your friends so that more and more people get benefited with these sessions. If you don't like the content, then also please comment in the comment section so that from the next session onwards, we will improve based on the feedback received from your side. So thank you. We will meet again with some new topic. Till then, thank you and goodbye.